Okay, and welcome back. So, remember last time we talked about how one of the distinguishing features, or one of the things that quantum mechanics can explain for us, is why electrons that are bound to atoms have very specific energies. And this concept applies to larger things than atoms as well. And in fact, one of the consequences of how it applies to larger things is the bedrock of a lot of modern technology. So I thought we would take a little detour and talk a little bit about it. But first, to set it up a little bit, we've got here, get my pointer, a picture of some of the atomic orbitals for hydrogen. Okay? Just a random few. And remember that these orbitals correspond to certain energies, and the picture of the orbital here represents the probability that electrons will be found at a particular point within that orbital. Or think about it kind of like an orbit, though as you can see, these don't look anything like the orbit of a planet around the sun or something like that. Okay, so just probability. So brighter means more probable. Okay, so they can have these certain energies depending on what orbital they're in, and their position is dictated by a probability distribution that is given by the shape of the orbital. These orbitals, by the way, are described by mathematical functions called spherical harmonics. Fun looking things, and you should look it up sometime if you have a chance, but you don't have to worry about it. Now, if you extend this to, this is a nice picture that I found of the molecular orbitals of an acetylene molecule. So you're talking about 2 hydrogens and 2 carbons, all chemically bonded together, covalently bonded together. And you can apply the quantum mechanical equations, and you can calculate what the molecular orbitals would be. So what the energies and positions of the electrons around the molecule, these bonded 4 atoms together, would look like. And you've got a bunch of them here. The ones in the top row here are lower energy and are generally occupied by whatever electrons you have. And then these are higher energy, more complicated ones that you might not always occupy, depending on whether or not it's been hit by a photon of light or something like that. Okay, but again, what these are representing, albeit in a little bit of a different way than we looked at with the atomic orbitals up here, is position and also probability. And the being in a particular orbital also makes it so that the electron would have a particular amount of energy. Okay? Now, if you take the molecules and you start stringing those all together, or if you take a whole bunch of atoms and you start stringing those together, you can start thinking about actual big chunks of material. And the way that the structure of solid materials is represented is by showing what's called a unit cell. Let me switch to my pen here. And what you're seeing here are these little BBs, these little balls that represent the positions of the nuclei of the atoms involved. This is the so-called unit cell of a crystalline silicon, chunk of crystalline silicon. And the idea is that the unit cell tells you a pattern of bonding between atoms of this substance that repeats itself over and over and over and over again to build up this crystal that, for instance, makes up a lot of solar cells. Crystalline silicon is present in the vast majority of commercial solar cells. Okay? The identity of the material is not really that important here, but more the idea that we've got these nuclei, okay? And then the little sticks between them all represent which ones are bonded. And the electronic structure, they don't actually put here because it's terribly difficult to visually represent, because as you can see in these acetylene molecules, the orbitals, even for a 4-atom molecule, get quite complicated and obscure the atoms or sort of the positions of the nuclei. So, I mean, you can imagine, though, that the electron clouds around these things kind of envelop all of that, but then, of course, they're enveloping both of these, and they're kind of shared in between all of these bonded atoms, and so you get these terribly complex looking clouds of electrons. There is some computer programs that can model these things in 3D, but they are difficult to look at in this format, okay? But you have, again, sort of orbitals that tell you what the energies and positions, well, at least the probability of a certain position of the electrons would be. Same idea, except in a much more complex material, because if we're talking about an actual piece of silicon that we could actually hold in our hand, then we're talking about many unit cells. And these unit cells are about, just to give you a sense, they're about a half a nanometer on a side, so 1/2 of 1/1000th of a meter. And so if you're actually holding a piece of silicon and you can actually see it, then, I mean, just think about that. That's maybe, I mean, say it's a small piece, so it's a centimeter on a side. That means you've got something like 10 to the 7th of these little unit cells of silicon atoms all bonded to one another. And what that looks like when you start building it up is like this. You just stack them, okay? So they're all, it's just this pattern repeats and repeats and repeats and repeats and repeats and repeats and repeats some more, and builds up to give you this crystalline structure where all of these atoms have these fixed positions relative to one another within this, what's called the crystalline lattice. What we want to focus on here, though, is the idea that because of all this chemical bonding between all of these atoms, and so many atoms are bonded to the others and are in proximity to the others, you get an electronic structure that isn't really well represented by pictures like these for the molecules or like those for the atoms. And so the physical theory that is used to put these things together talks about the allowed and disallowed energies of the atoms, or rather the electrons around the atoms, and in this crystalline structure, talks about it in terms of bands. And let's talk a little bit about what that means, okay? So if you're thinking about the energies of all of these electrons bound to these atoms, and remember, the energies correspond essentially to how closely bonded these electrons are to the atom. If you're looking at that, let's for a moment concentrate on this part of the diagram. Okay? You don't have to worry too much about things like Fermi energy, okay? But these are the bands. Okay? So if an electron is in the conduction band, well, what that means is that the electron is reasonably free to move through material. So, for example, metals, over here on the left, have lots of electrons that are always present in the conduction band. So this valence band that's full of electrons overlaps with the conduction band in blue here. And so there's always some portion of the electrons in a conductor, in a metal, that are free to move around through the thing. So that's why, for example, in all of our electric circuits, we make them out of things like copper and aluminum and things like that, so that we can move the electrons that carry the electrical energy through those materials easily. Okay? Now over here on the right, the thing that I've sort of boxed in here, we're talking about an insulator, and that is just the opposite situation. You've got all these allowed energies, so the energies here in the conduction band, those are all allowed, and the energies here in the so-called valence band are all allowed. But in an insulator, unless something quite unusual is happening, all of the available states in, and here, let me change my pointer color because red won't show up on that thing. All of the available energy states, all packed close together, okay, in this valence band are occupied. Okay, so you've got electrons in them, it's because they're below the Fermi energy here. And up here, I mean, yes, technically these energies are allowed in the conduction band for an insulator, but you have to give the electrons in the valence band a lot of energy to actually get them to go up there and start moving around. Okay? In principle, it could happen, but in actual fact, insulators, things like rubber and plastic, what they coat electrical wires in and what you use to keep yourself safe from electrical shock and things of that sort, conduct no electrons. Electrons can't move freely through them because all these conduction band energies are allowed because of the way that the electrons are configured around the atoms. It's very difficult to get electrons into that conduction band. Right? And this difference in energy between the sort of top of the valence band and the bottom of the conduction band, so top of the valence band being where the electrons are bound to the atoms tightly, they're not going to go wandering off through the material and they're not free to move, and the bottom of the conduction band being the lowest energy state where an electron, if it occupies that state, can freely move through the material. Okay? The difference in those energies, right, is called the band gap. Okay? And chemists have a different word for it, but we'll call it the band gap, and that's the usual thing. Okay? And that difference in energy, that band of energies in there, okay, the band gap, means that none of these energies are allowed. Electrons simply cannot exist there. Now, if we didn't know about quantum mechanics, we would have no explanation for, well, we probably wouldn't even know that the band gap was there. We would lack the ability to describe the material enough to know that this is what was happening. But quantum mechanics is the thing that tells us that, okay, well, you've got a certain bunch of states in which the electrons can do certain things that are allowed. You can have those energies. And you've got a bunch of states here where the electrons are allowed to do different things. Well, usually not allowed to do things like move around in the material, okay, that are allowed according to the quantum mechanical function that describes all of these energies. And then you've got this whole area in between, the band gap, where electrons cannot exist, okay, in terms of energy. Okay, now an insulator is not terribly interesting because this band gap is such a large energy that you really have to put in a ton of energy and go to a lot of work to get any electrons at all to go into the conduction band and be allowed to move through a material. Okay? Now, the interesting class of materials here is what we've got right here in the middle, semiconductors. Okay? And you can see that these two allowed sets of states, so the conduction band and the valence band, do not overlap like they do in a metal. So by default, you got a piece of silicon just sitting there, you generally don't have any electrons sitting around in the conduction band and free to move around. So a semiconductor does not allow electricity by default to conduct through it. Sort of the name implies that, semiconductor. But this band gap, right, this energy gap between the bottom of the conduction band and the top of the valence band is so small in the family of materials called semiconductors that you can put in just a little bit of energy. You can fiddle with them just a little bit in a lot of different ways, and you can convince electrons to go from the valence band, where everything is filled and everything is bound to the atoms and all our nuclei and all of that kind of stuff, and it can't freely move. You can induce electrons pretty easily to pop up into the conduction band and do things that you want and move through the material. So the idea, the band gap, the fact that semiconductors have this band gap and that it's of a certain size so that we can manipulate these materials to make them conducting and allow electrons to move through them, or to not allow that, depending on what we do to the material, is they can do a lot of things for us. They're the basis of a lot of modern technologies. One we won't go into here is the photovoltaic cell or solar cell. And you use semiconducting materials in that and allow sunlight that, let me erase all of my lines here. There we go. Okay. When you have, let's say, a silicon solar cell, you have photons of light that come in and hits the surface of the solar cell. And those photons of light have a certain amount of energy. And if the photon of light has enough energy to bridge this band gap, right? If it happens to pop in here, hits a particular electron that's sitting in the valence band bound to its nucleus, and gives it a certain amount of energy, right? If the frequency of this photon of light is high enough, then it can give that energy to the electron and promote it into the conduction band and allow it to move around. And it leaves behind what's called a hole, literally a hole, like where the electron used to be. And it acts kind of like a particle because everything else is filled up with electrons, so it's like a positive particle, quote unquote, in there. And if you can, in a solar cell, separate those charges, that positive and that negative electron in the conduction band and that positive hole in the valence band that are now wandering around, then you can net some electrical energy, and you can, power the power grid with an electric, solar cell farm, or you can, power your house or something like that. Okay. We won't go too much into that application. I'll talk about one other one here. Semiconductors and the presence of the band gap are integral to LEDs. LEDs are everywhere. They're the reason we can, read Blu-ray discs. They're the reason we have all these flashing little lights on things. Modern light fixtures are all LEDs, or at least the more expensive and durable and energy efficient ones are, and they rely on the band gap. So it's diagrammed here. So here's the band gap, and they sandwich two different types of material together, essentially. So you imagine that the border between one type of material and the other type of material is here. So you've got one type of material over here, you've got another type of material over there, and you have an excess of electrons in one material, and you have an excess of holes, so gaps from electrons not being there in the valence band of the other material. And when they are brought together, when you apply a sufficient voltage to these, so electrical energy to these, then the electrons in the holes, because they're oppositely charged, they are attracted to one another and they tend to recombine. And when they recombine, then it kicks out, as the diagram kind of implies, photons of light at a specific energy that matches the gap between the energy of the hole and the energy of the electron, between the conduction and the valence band in these materials. One other very important application of semiconductors and this band gap, this big bunch of disallowed energies within semiconductor materials, is the transistor. This is a specific kind of transistor called a field effect transistor. The basic idea is that if you apply an electrical signal to the gate, then you can cause this area right here, it's called the channel, okay, to either allow electrical energy to pass through, okay, so allow electrons to move through there and a current to go through there, and so it acts like a conductor. Or you can tune the energy on the gate to make it so that nothing happens. Okay? If you think about that, that's kind of like a switch, but instead of actually manually having to go over and flip the switch, you are allowing an electrical signal applied here at the gate to turn on and off this switch, to open and close this channel between what's called the source and the drain in a transistor. Now, the transistor came into existence, or was discovered, around, when was that? I think sort of early 1950s, and was pretty quickly recognized as something that could replace and improve a lot of existing technologies. And these days, well, actually, this is a computer chip made by AMD back in the late 90s, so we've come even farther since then. But on this computer chip, you've got literally millions of these transistors, all these little switches acting in concert, which causes the little electrical signals coming in on all of these wires here. Okay, so each one of these little tiny things is a wire. Okay? So you type a key on a keyboard, it goes through the software of the operating system, it gets interpreted and distilled down to an electrical signal on the circuit board. It comes into one of these wires and sets off a cascade of digital logic. It's all based on these little electrically operated switches, these transistors, okay? And does all the calculations it needs to, like, you hit the J key on your keyboard and then suddenly there's a J on your document on there, or you type some numbers into a calculator and tell it to go, and it all runs through this chip, and that's That's how a lot of modern technology works. Everything from our phones up to the supercomputers and servers that drive the modern internet. And it's all based on the band gap in a bunch of semiconductor materials, silicon for the most part, okay? And packaged into these fabulously complex chips. I mean, this is from the late 90s, so this is probably, maybe 100 million transistors on this chip here, okay? On this chip that I'm talking about, in case you're not seeing my pointer. These days, you've got billions and billions and billions of them because they've managed to make these transistors extremely small. I think the latest technology has the smallest dimension of these transistors being something like 7 nanometers, so 7 billionths of a meter. And to give you a sense of scale, and one I think I've used in the class before, a human hair is like 50 to 100 millionths of a meter in diameter. So you're talking about transistors, these little electrically operated switches, that are 10,000 times smaller than the width of a human hair, thereabouts. It's bananas, and yet all based on understanding the band gap, which is a consequence of quantum mechanics. So when we come back next time, we'll go back a little bit to we'll back off the applications a little bit. We'll talk a little bit about more about quantum theory and some of its basic concepts to give us a little more grounding there. And that's probably going to bring us about to the end of the unit and the end of the course. So it's a little bit sad, but hopefully this all was making sense. And if not, remember to drop into my office hours, and I will see you then.